In this video, we're going to look at a few more examples of the limit comparison test. Test the following series for convergence or divergence. Question A, summation n equals 1 to infinity 2n plus 3 times e to the minus n divided by square root of 4n to the 6 minus n. Question B, summation n equals 1 to infinity sine of 1 over n. We have two different series, and our job is to apply the limit comparison test to determine whether these series converge or diverge. Let's look at question A first. Notice as n goes to infinity, the dominant part of the numerator, is 2n, because this part 3e to the minus n is going to approach 0 as n goes to infinity. 3e to the minus n is equal to 3 divided by e to the n will approach 0 as n goes to infinity. Now let's look at the dominant part of the denominator. The dominant part of the denominator. Now the denominator is the square root of 4n to the 6 minus n. The dominant part of the denominator is square root of 4n to the 6 because n is much smaller than 4n to the 6 for large n. So as n goes to infinity, 2n plus 3e to the minus n, which is a general term of our given series, divided by square root of 4n to the 6 minus n, will be approximately equal to 2n divided by square root of 4n to the 6, which is equal to 2n divided by 2n cubed. The 2's cancel out, and we get n divided by n cubed, so we get 1 over n squared. So this is our comparison series, summation 1 over n squared, which, by the way, is a convergent p series, p equals 2, larger than 1. So we should apply the limit comparison test. We're going to apply the limit comparison test with an, which is the general term of our given series, 2n plus 3e to the minus n divided by square root of 4n to the 6 minus n, and our comparison series is bn is equal to 1 over n squared, which is a convergent p series, p is equal to 2. So now let's take the limit as n goes to infinity of an divided by bn. This is equal to limit n approaches infinity, 2n plus 3 e to the minus n divided by square root of 4n to the 6 minus n divided by 1 over n squared. Now, when we divide by 1 over n squared, that's the same thing as multiplying by n squared over 1. So let's just rewrite that times n squared over 1. Let's simplify that. We get limit n approaches infinity, 2n cubed, multiplying the n squared through, plus 3n squared e to the minus n divided by square root of 4n to the 6 minus n. So we have limit as n approaches infinity of 2n cubed plus 3n squared times e to the minus n. Let's write it as divided by e to the power of n, all divided by square root of 4n to the 6 minus n. So let's divide by the dominant term in the denominator, which is, of course, n to the 6, the highest power of n. But if we divide by n to the 6 inside a radical, this is equivalent to dividing by n cubed outside the radical, because square root of n to the 6 is equal to n cubed. So let's divide by n to the 6 inside the radical, divide by n to the 6, and divide by n cubed outside the radical, divide by n cubed. And let's simplify. We get limit as n approaches infinity of 2, because n cubed cancels, plus 3 divided by n times e to the n, divided by square root of n to the 6 cancels, we get square root of 4, minus n divided by n to the 6 gives us 1 over n to the 5, 1 divided by n to the 5. Now, when we take the limit as n approaches infinity, 3 divided by n e to the n is just going to approach 0 because you have a constant in the numerator and n e to the n in the denominator grows to infinity. For the same reason, we have 1 divided by n to the 5 constant in the numerator dividing by something that grows to infinity. The ratio approaches 0 as n approaches infinity. So the ratio limit as n approaches infinity of an divided by bn is equal to 2 plus 0 divided by square root of 4 minus 0. This is equal to 2 divided by root of 4, which is 2. 2 over 2 is 1. It's a constant greater than 0. Since limit as n approaches infinity of an divided by bn is equal to 1, which exists, is a constant, and summation bn n equals 1 to infinity is equal to summation n equals 1 to infinity 1 over n squared, which is a convergent p-series, is a convergent p-series with p equals 2 greater than 1. The given series is also going to converge by the limit comparison test. The given series summation n equals 1 to infinity 2n plus 3 e to the minus n divided by square root of 4n to the 6 minus n also converges by the limit comparison test. Let me write it on this page as well. Summation n equals 1 to infinity 2n plus 3 e to the minus n divided by square root of 4n to the 6 minus n also converges by the limit comparison test. Also, we always have to state this sentence at the end of the question, at the end of the solution to the question. Also converges by the limit comparison test. Now let's look at part B, question B. Here we have summation n equals 1 to infinity sine of 1 over n. Since we have 1 over n inside the sine function, this suggests that we should apply the limit comparison test with Bn is equal to 1 over n. This is our comparison series, which, by the way, is a divergent p-series. P is equal to 1. And an is the general term of our given series, which is sine of 1 over n. So this is where the intuition comes in. We saw 1 over n inside the brackets, and we said let's choose our comparison series to be Bn is equal to 1 over n. So now let's write this as limit as n approaches infinity, an divided by bn. This is equal to limit as n approaches infinity, sine of 1 over n divided by bn, which is 1 over n. Now we're going to apply a trick here. We're going to let u be equal to 1 over n. Notice when n approaches infinity, u approaches 0 because u is equal to 1 divided by n. U approaches 0. So we have the limit as n approaches infinity of an divided by bn is equal to limit as n approaches infinity of sine of 1 over n divided by 1 over n, which is equal to limit as u approaches 0 because we made a substitution. U equals 1 over n. Sine of u divided by u. So what we have is a limit as n approaches infinity. Limit n approaches infinity, an divided by bn. We're applying the limit comparison test. This is equal to limit as u approaches 0, sine u divided by u. Now notice we have the 0 over 0 pattern. That means we have to apply L'Hopital's rule. So we're going to apply L'Hopital's rule to evaluate this limit. L'Hopital's rule. So we have limit as n approaches infinity, an divided by bn. This is equal to limit as u approaches 0, sine u divided by u. Now apply L'Hopital's rule. That means take the derivative of the top, divide by derivative of bottom. So that's limit u approaches 0. What is the derivative of sine u? Derivative of sine u is cosine u. And derivative of u is just 1. Now take the limit as u approaches 0. Cosine 0 is equal to 1. And this is a constant. 1 is a constant greater than 0. So we say since the limit as n approaches infinity of an divided by bn is equal to 1 larger than 0, this limit exists. And our comparison series summation bn n equals 1 to infinity is equal to summation n equals 1 to infinity 1 over n. And this comparison series is a divergent p-series. Divergent p-series with p equals 1. So therefore, the given series that we have, which is summation n equals 1 to infinity sine of 1 over n, also diverges by the limit comparison test. Also diverges by the limit comparison test. So that's the general idea of the limit comparison test. All right, thanks.